Welcome to this lecture whereby we are going to look at halogens that are used as germicides. And these are chlorine and its oxo compounds. Then we have iodine and the related compounds. After that, we look at potassium permanganate. What is common among these is that they are oxidizing germicides. The objectives of this presentation are: number one, to study chlorine and related compounds that are used as germicides. Number two, to study iodine and related compounds that are used as germicides. Then number three, to look at potassium permanganate as a germicide. Then last but not least, to look at sample questions. We start with halogens. Halogens are in group 17 on the periodic table, and we'll cover chlorine and the related compounds, and then iodine and the related compounds. Look at halogens. Chlorine is a halogen and it is an oxidizing germicide. Note that not all halogens are germicides, and these halogens are used as germicides in their zero or positive oxidation states, and the germicidal action is accompanied by reduction of the halogen to the lowest negative oxidation state. And the germicidal activity is restricted to elemental chlorine and iodine together with their oxo compounds. That means that iodine has germicidal activity, while iodide ion has little or no germicidal activity. So bromine and oxobromates are active germicides. However, they are a bit expensive, and chlorine compounds and elemental iodine and the correlated compounds are readily available, and those are some of the reasons why they are mostly used. And the compound of chlorine that is commonly used is sodium hypochlorite. Under chlorine and its related compounds that are used as germicides, we look at chlorine itself, sodium hypochlorite, calcium hypochlorite, lithium hypochlorite, and chloramine. So chlorine is a halogen that is used in disinfection. It has strong oxidizing properties, which allows it to kill bacteria, viruses, and other pathogens. It is commonly used in water treatment. For example, you can treat swimming pool water and also drinking water. It is also used in sanitation. It is effective, affordable, and has a long-lasting impact. How does chlorine work? It works through oxidation. It is an excellent oxidizer. It is able to penetrate the microorganism cell wall and disrupt essential cellular components. This renders the pathogen inactive, and it can also lead to its death. It also works through formation of hypochlorous acid, whereby when it is added in water, it reacts to form hypochlorous acid, which is more effective in killing pathogens than chlorine alone. Hypochlorous acid disrupts the lipid layers of viruses and bacterial membranes. It also acts through residual protection, whereby it has the ability to provide residual level of disinfection, hence can continuously kill pathogens as they enter the treated water. Then we look at sodium hypochlorite. It is a chemical component of the household bleach. It is used as a disinfectant. So when this sodium chloride comes into contact with water, it ionizes to give sodium, hypochlorite ion, and hypochlorous acid. Hypochlorous acid has germicidal activity, and this hypochlorite ion is usually in equilibrium with hypochlorous acid. So at pH 4 to 7, chlorine exists predominantly as hypochlorous acid, and then above pH 9, you get the hypochlorite ion predominating. How is sodium hypochlorite prepared? It is prepared through electrolysis of brine, and brine is a solution of sodium chloride. So in that solution, sodium chloride dissociates to give you sodium cation plus chloride ions. Then your water dissociates to give you hydronium ions plus hydroxyl ions. The negatively charged ions move towards the anode, while the positively charged ions move towards the cathode. The end result is that your sodium chloride will react with water and electricity in the presence of electricity to give you sodium hypochlorite and hydrogen gas. You can add sodium hydroxide sometimes to maintain the alkalinity or the alkaline pH, because this pH slows down the composition of sodium hypochlorite. It actually makes it stable. A pH above 11 is actually optimal often. This slide shows electrolysis of brine to generate sodium hypochlorite. So we have water, which dissociates to give you hydronium ions plus hydroxyl ions. Then you have sodium chloride, which dissociates to give you sodium ions plus chloride ions. So the negatively charged ions move towards the anode, while the positively charged ions move towards the cathode. Remember, the anode is positively charged. So at the cathode, you will get hydrogen being produced, and at the anode, you'll get chlorine being produced. So sodium hydroxide reacts with chlorine to give you sodium hypochlorite, sodium chloride, and water. So the possible contaminant of this sodium hypochlorite is what? Sodium chloride. We look at the other possible contaminants. So the impurities that you can find in sodium hypochlorite include sodium chloride, which is created as a result of the production process. Then you have sodium hydroxide, which can be added to stabilize sodium hypochlorite and prevent its decomposition. Then you have sodium chlorate, metals, and other organic impurities. So you can get sodium ferrate in sodium hypochlorite, and it imparts color to your sodium hypochlorite. And then normally the concentration that you'll get of sodium hypochlorite is between 4 to 6%. And the germicidal action of sodium hypochlorite is improved by reducing its pH. So pH plays a very, very important when it comes to stability of sodium hypochlorite. So when the pH is around 12, your sodium hypochlorite will be very stable. If you want to get germicidal activity, you have to ensure that your pH is between 6 to 8. So hypochlorite ion reacts with acid to give you hypochlorous acid. Remember, hypochlorous acid is the one that has germicidal activity. And hypochlorous acid is more effective as an oxidizing agent than the hypochlorite ion or chlorine itself. Look at hypochlorous acid. The formula is HOCl. It is relatively unstable and can decompose due to several factors, which include exposure to light. So it is sensitive to UV light, which accelerates its decomposition. Temperature also increases the rate of decomposition, and also presence of catalytic ions or metals such as copper, iron, or nickel. They actually act as catalysts, and they enhance the breaking down of hypochlorous acid. pH levels also determine the stability of HOCl. Note that chlorine 1 compounds are excellent disinfectants and have decolorizing action, and in neutral and slightly acidic media, they are very useful as germicides. And then unadjusted solutions of sodium hypochlorite are unsuitable for application to wounds because the high pH is destructive to the tissues. And then the solutions are relatively non-selective towards microorganisms. And the pathogens of the colon, the ones that cause typhoid, and many pathogenic spores are sensitive to these compounds. Even the large viruses, which are filterable, are usually inactivated. The effectiveness of these compounds can be decreased in the presence of organic matter because chlorine has a high affinity for the protein molecules. Then sodium hypochlorite solutions may be rendered suitable for use in wounds by adjusting the pH downwards. We look at Dakin solution. What is it? It contains sodium hypochlorite and boric acid. This boric acid helps to maintain a pH level between 9 and 10, which is less irritating. Dakin solution is effective against a wide range of organisms, including bacteria, viruses, fungi, spores, and methicillin-resistant Staphylococcus aureus. And it is a topical antiseptic that is used to treat and prevent infections in wounds. You can actually buffer sodium hypochlorite. So, sodium hypochlorite solution must be buffered before use, and the most commonly used substances that can be used to buffer are boric acid and sodium bicarbonate. Then we look at calcium hypochlorite. It is a white inorganic compound. It is also known as chlorinated lime. It is composed primarily of calcium hypochlorite, and often it has some calcium chloride and calcium hydroxide. It is one of the most effective and the least expensive chemical disinfectant known, and it is used in water treatment and also as a bleaching agent and wastewater treatment. Calcium hypochlorite is an important disinfectant, and it is also effective for water treatment. Look at lithium hypochlorite. It is an inorganic compound and a powerful oxidizing agent. It is used as a disinfectant and a bleaching agent. It is less commonly used since it is costly and also prone to decomposition. Then we move to chloramines. From the word, what are chloramines? They are chlorinated amines, and when put in water, they release hypochlorous acid. Remember that hypochlorous acid has germicidal action. So how are they prepared? They are prepared by reacting the amine with chlorine. And they are derivatives of ammonia by substitution of 1, 2, or 3 hydrogen atoms with chlorine. So the action of this group of compounds is therefore similar to that of chlorine water and the hypochlorites. So we look at preparation of chloramines. You can take hypochlorous acid and then you react it with ammonia. And how do they work? The chloramine, when put in water, releases hypochlorous acid, and it is the hypochlorous acid that is responsible for germicidal action. Chloramines are relatively stable and they release chlorine over a longer period of time. So a chloramine is a weaker disinfectant compared to chlorine because of the slow release of hypochlorous acid. And chloramine solutions are more stable than hypochlorite solutions of similar strength. And since the hypochlorous acid is released slowly, inactivation by organic matter is not as apparent. What are the uses of chloramines? Chloramines are used to disinfect drinking water and also waste water. So note that if you have the chloramine and you want to make it tangible, you can use sodium chloride to act as a base. That one you can add. That photo shows you halazone tablets, which are examples of chloramine. When we look at an example of a chloramine, we have halazone. It is a white powder or crystal with chlorine odor. It is slightly soluble in water and chloroform, and it is used to disinfect drinking water. And it is a chloramine, a type of chlorine releasing compound used as a disinfectant. So we have another example of a chlorine containing compound, that is sodium dichloroisocyanurate. One of the examples in the market is Precept, and you can use NaDCC to represent sodium dichloroisocyanurate. It is a stable source of chlorine that is used to disinfect water, swimming pools, and also in the food industry. It is also used in household water treatment systems. We look at sample questions. Number 1, give 4 factors that influence the efficiency of germicides. Number 2, discuss factors that should be considered during the selection of germicides. Number 3, write short notes on halazone. Number 4, list 3 compounds of chlorine that are used as germicides. Number 5, explain 3 factors that affect the stability of hypochlorous acid. And last but not least, we have using equations, show how chlorine is used to disinfect water. Remember, this is part 1 of halogens that are used as germicides. We'll also have part 2. We've basically covered chlorine and its compounds. So part 2 will cover iodine and its compounds. Thank you for watching.